You learned it as a chant. A squared plus b squared equals c squared. You've plugged numbers into it for years, but why is it true? And why does it only work for right triangles? This is symmetry. Let's find out why. First, what the theorem is actually about. Here's the part most people miss. Those little squares in the formula aren't just notation. They're real squares. Build an actual square on each side of a right triangle. The theorem says something almost unbelievable. The area of the two smaller squares added together exactly equals the area of the big one on the longest side. It's not a fact about lengths, it's a fact about areas. And people were using this long before Pythagoras. Over 1,000 years before Pythagoras, Egyptian rope stretchers carried a loop of rope with 12 evenly spaced knots. Fold it into sides of 3, 4, and 5, pull it tight, and the corner between the 3 and the 4 is a perfect right angle. Every time. They didn't have the proof, but they trusted the pattern enough to lay the foundations of temples with it. Now the proof, and it fits in a single picture. Take a big square with a side of a plus b. Now fill it with 4 copies of our right triangle, arranged one way. What's left over is a single tilted square, and its side is the hypotenuse, so its area is c squared. Now take the very same big square and the very same 4 triangles and just slide them into a different arrangement. This time, what's left over is 2 upright squares. One of area a squared, one of area b squared. Same big square. Same. Let's say that in symbols. Both big squares have the same total area. Both hold the same 4 triangles. Subtract those triangles from each, and whatever remains must be identical. On one side, that leftover is c squared. On the other, it's a squared plus b squared, so they are equal. A squared plus b squared equals c squared, not a rule to memorize, a leftover you can see. But here's the subtle part everyone skips. This only works when the angle is exactly 90 degrees. Open that corner a little wider, and the longest side stretches, so c squared grows larger than a squared plus b squared. Close it a little, and c squared falls short. The equality balances on a single, perfect right angle. That's not a limitation. That's what makes the right angle so special and so useful. And this is where it stops being about triangles. Put 2 points on a grid. To get from one to the other, you go across and you go up. That horizontal gap and that vertical gap are the 2 legs of a right triangle. And the straight line distance between the points, that's the hypotenuse. So the distance is the square root of delta x squared plus delta y squared. Every time you measure a straight line distance, you are secretly using Pythagoras. And it doesn't stop in 2 dimensions. Add a 3rd axis, and the same idea gives the distance through space. Physicists even use a version of it to measure distance through space and time itself. A rule the rope stretchers stumbled onto 4,000 years ago turns out to be woven into the shape of reality. So a squared plus b squared equals c squared was never a spell to memorize. It's 4 triangles moved across a square, leaving the same space behind. If that gave you a small jolt of, oh, that's why, then that's exactly what symmetry is for. Subscribe, and every week we'll make one more piece of math or science click. And if it did click, a like helps it find the next curious person.